It's good to see you all here, and I'll be brief too because, as we all know, time is of the essence. And it's the time we will spend with our speakers that's most important here. The basic format is each person will speak for 30 minutes and then there'll be 15 minutes of questions afterwards. Our first speaker is Harvey Brown, and I do have to mention that there's a significant Southern Hemisphere aspect to his development. He did his early work in physics at the University of Canterbury in New Zealand. There was a graduate student in London, and he taught also in Brazil before returning to Oxford to teach in the philosophy department here with strong links with the physics department. He's particularly known for his work on Einstein, relativity, philosophical foundations of quantum field theory. That's the title of one of his important edited books. Also a very important edited book on the philosophy of the vacuum. And more recently, a highly constructive, creative reading against the grain in an account of what he called physical relativity, space-time structure from a dynamical perspective that was really interesting for both philosophers and historians of relativity. So with no further ado, I'd like to welcome Harvey Brown.
Is that open now? Can people hear me? First of all, let me thank Richard for that extremely nice introduction. And I'd like to thank Joe Ashbourne for the invitation to speak today on this question of time, which is a subject very close to my heart. I understand my job today is to be basically a warm-up act. This is a taster. It's going to be more of a romp than a survey. It's a vast subject, and I'm going to run through some of the ideas that I think are so important. What is it about time that makes it such an elusive and confusing issue, concept? Well, we can't do better than to quote St. Augustine in a famous saying, "What then is time if no one asks of me, I know. If I wish to explain to him who asks, I know not." Let's think of a few slogans. The first one is a slogan that I've seen attributed both to John Wheeler and to Albert Einstein: time is what stops everything happening at once. Now, another way of putting the same point is that time is nature's way of getting around the law of non-contradiction. My hand is up, my hand is down. They're contradictory statements. Magicians don't like contradictions, but nature has found a way of getting around them. This one was first and this one was second. So this gives us a sense that time has something to do with multiplicity. Different arrangements of the world, we're allowed to have contradictory arrangements because we say they occur at different times. As a first approximation, that's not a bad grip on time. But of course, it doesn't give us a notion of duration, a metric, simultaneity, and all those further aspects. One slogan that I like very much: instants are not in time, time is in instants. And I'll come back to this later in the talk, by Julian Barber. Well, of course, the most profound and the most significant of all of these slogans, of course, is time is money, but I don't think we'd better go there today. I was amused when I was preparing this talk, trying to find who first came up with this, and this is widely attributed to the great Benjamin Franklin. And I'll come back and say a bit more about it. Benjamin Franklin will appear a little bit later in the talk. In physics, time is not just one thing, it's multifaceted, and that's basically the sort of topic of my talk today. But I'm going to try to argue that it's not a thing at all. Time is not a thing. There are many aspects of time, and I'm going to say in a way that it can't be measured. Now, on the left here you see a picture of the face of a clock, and you think to yourself, well, if a clock isn't measuring time, what is it measuring? But think of it the following way, just to get our thoughts running. A thermometer is a measuring device for the temperature of your body, say. And what you do is you take this device, let's say it's an old-fashioned mercury thermometer, and you attach it to your body somewhere or other. And there's an exchange of heat, and the mercury changes its length of the thermometer, and that gives you some reading of the temperature of your body. There's an interaction between the measuring device and the object it's measuring. What is time? What is a clock interacting with? What is it measuring exactly? Bear that question in mind. I think to think of time as being a straightforward measurement in the sense that it's the thermometer of time is going to lead to all kinds of problems that we see later in the talk. So I'm going to say a little bit about the arrow of time, the fact that we can distinguish before and after. I'm going to say a little bit about simultaneity, its two faces, one that it's conventional, essentially, and the other that it's relative. The relativity of simultaneity is something that's attributed originally to Poincare and Einstein. Then a little bit about the connection with clocks, duration. Time is a metric. So between my hand being down and my hand being up, a certain amount of time passed. How much time? How do we measure the duration of time? How do we define it? What's the connection with clocks? And then what do clocks do, for example, when clocks are in motion? And this again brings us to Einstein. So the last part will be duration. Motion, dilation, what happens to clocks when they're moving, and what happens to clocks when they're at different heights, say in the Earth's gravitational field. So just a quick word about the hour of time. Anyone recognize? Well, I'm sorry, this is not a very good appearance of the photo. This is a photo of Einstein's office at the time of his death in 1955. And you look at this photo and you see a lot of history in there. It contains a lot of information about the past. And in fact, on one of his ledges, you can see pretty much an entire, there's probably a major physics journal in which he has all of the issues. And of course, in that range of issues of this physics journal, there's an enormous record of thoughts, writings, publications in the past. Why do we see in the photo something about the past and not the future? I mean, the wonderful thing about physics is it makes us wonder sometimes about things we otherwise wouldn't wonder about. The fundamental laws of physics, with one minor exception, which we shouldn't get hung up on, the fundamental laws of physics do not know the difference between the future and the past. They're what's called time reversal invariant. Why is it then that we are completely in our daily lives surrounded by something that looks time asymmetric, our memories of the past and not the future? Why is this? Well, of course, this is something to do with the second law of thermodynamics, but if you think that this is something that we experience partly because we're so complex and so on, we have memories, brains and memories and so on, think of the humble plant. A humble plant like the Arabidopsis, something that's being studied enormously by geneticists in plant science. This is a simple plant, very common both south and north of the Alps. It acts as a stopwatch and it has memory also. It acts as a stopwatch in the following sense. Think of a day in the autumn and a day in the spring. They have roughly the same length, they have roughly the same temperature, the same sunlight. Why does the plant flower in the spring and not in the autumn, particularly if it's north of the Alps? Why is this? Because the plant has a gene that suppresses flowering, but during the winter, it records something like 40 days of a temperature between 2 and 4 degrees, and its memory of that duration of cold, how it measures this we don't know, suppresses the gene that suppresses the flowering. So it's acting like a stopwatch. But further, once the spring comes and the daylight increases, it triggers the flowering. So what happens if you take this plant and put it in darkness in spring? Well, it turns out that this particular plant, unlike many others, remembers the length of winter for some months. Other plants don't. So this particular plant also has memory. And again, of course, it's memory about the past. Is the entropic arrow of time? Of course, this all comes back to essentially the second law of thermodynamics. Actually, it's not even the second law of thermodynamics. It's something even more fundamental in thermodynamics. Systems out of equilibrium tend towards equilibrium spontaneously. This is the fundamental time asymmetric feature of the world. We see it around us all the time. Can we understand this on the basis of time symmetric laws? We can, but it's not the laws themselves that are doing the work here. It's only part of the work. Of course, the other part is the initial conditions of the system or maybe the universe. So there's no absolutely paradoxical thing going on here, but there are many puzzling aspects. And to me, the most puzzling of all is, why do we see so many systems that are more or less autonomous, isolated, around us, not only in our daily lives, but across the universe? Why do we all see them starting in low entropy and showing the same hour of time? Why don't we see some systems using the opposite hour of time? Well, this is essentially a cosmological problem. And I'm going to leave it at that. But this is something that's given rise to an enormous amount of discussion, particularly in the philosophical literature. How to understand the arrow of time, given that the fundamental laws of physics don't know the difference between the future and the past. Okay, let's romp on to simultaneity. Remember, a clock has basically two features to it, amongst others. The fundamental two features are, first of all, it acts like a stopwatch. It tells you, for example, how long it takes for me to give this talk. That's the metric notion. But it also tells me when I should start giving the talk. That's the phase of the clock. It tells me what time it is. So simultaneity is the question about how it is that I establish that the time over there is the same as the time over here. So I can say events occurring in those two places are either simultaneous or they're not. In other words, how do we spread time across space? Well, here's a picture of time zones across the surface of the Earth. This is one way that we spread time across space. And we look at these time zones and we think to ourselves, well, they're pretty conventional, and we could have done it slightly differently. Of course, the reason that we spread time across space in this particular way is well known. The Earth is rotating. We don't want, for example, 12 a.m. to occur as the sun is rising. So we're going to change our phases of our clocks as we go across the surface of the Earth. But what this reminds us is, first of all, this is a question of convenience. And secondly, as a result, we may end up traveling backwards in time. Any of you who have been to Australasia and flown, for example, to the Americas, you realize that you arrived before you left. And yet your head doesn't explode. You've just traveled backwards in time, but you're none the worse the wear apart from jet lag. Now, all right, clearly, I mean, this is a result of some kind of human artifice. You're crossing the international date line. But then it makes us ask, well, what's the true story of simultaneity? This is all convention. If I have an event occurring in Rio de Janeiro and I have an event occurring in London, are they simultaneous or not in some absolute sense? And we ask ourselves, well, how would we know? Well, we could take clocks together, or we could synchronize them together, and we can move them apart to the two regions, and we could say, well, then, depending on whether the events have the same times, they're simultaneous or not. But how do we know that the movement of the clock doesn't change somehow its functioning? We have to be careful here. We have to be careful. So here's one way we can test, just locally. Here are two synchronized clocks. I can see that they're synchronized. What more do I want? I may have moved them apart, but now I can check at some distance apart whether they're synchronized. Well, I just look. But are they? You see, that clock on the left is a little bit further away than the clock on the right. Should have taken a little bit longer for the light to reach you than on the right. So they're not really synchronized. But in doing so, in saying that they're not exactly synchronized, and physics wouldn't be physics if we weren't trying to be accurate. In saying that not exactly synchronized, we've been assuming something. We've been assuming that the speed of light coming from that clock to reach our eyes is the same as the speed of light coming from that clock to come to our eyes. How do we know that? Can't we measure the speed of light? If you're going to measure the speed of light, you have to know how far the light goes, and you have to know what the time difference is between the point of emission and the point of arrival. You need synchronized clocks. Looks like we ended up in a kind of a circle, a vicious circle. We cannot measure the one-way speeds of anything without having synchronized clocks. And that's exactly the problem we started with. How do we synchronize them? Well, we just bite the bullet. In physics, we bite the bullet and we say time is standardly spread through space. We're going to have to introduce a convention such that the one-way speed of light is the same in all directions. That's how we essentially spread time through space in physics. We just choose this as a convention. It's a good convention because it's simple. And we know, by the way, we can actually do measurements to show that the two-way speed of light is independent of direction. That's just the famous Michelson-Morley experiment. The question is, what about the one-way speed? Well, let's make life simple for ourselves and assume that the one-way speed of light is the same in all directions. That's how we spread time through space, essentially, in physics. And this is understood by Poincaré and later by Einstein. And it simplifies our equations in physics. But it's a convention. Now, let's talk about its relativity. Poincaré, even before Einstein, realized that if, for example, I'm doing an experiment in my laboratory and I've set up a coordinate system that tells me, for example, whether this event is simultaneous with that event, And that coordinate system is consistent with the Einstein-Poincare convention for synchronizing clocks. And Dr. Ashburn is passing me in a rocket, moving quite a speed, doing experiments in her laboratory. And then we're looking at two particular events that are occurring, and I say they're simultaneous because I've synchronized my clocks using the Einstein convention. And Dr. Ashburn looks at the two events, and she's synchronized her clocks using the Einstein convention, and it turns out that we don't agree. And that's a prediction of relativity theory. We simply don't agree. Is this mind-blowing? Well, it's very counterintuitive. You would have thought that if two events are simultaneous, they're simultaneous, period. But remember, simultaneity, we already realized, was a convention in the first place. So if two observers are using the same convention, it doesn't necessarily mean they're going to agree on simultaneity. That's the relativity of simultaneity. But then you see, suppose I want to say, okay, how I synchronize my clocks, everyone agrees about that, it's that we use the same convention, but if we're in different states of motion, relative motion, we may disagree on which distance events are simultaneous with my local events. So when I want to say, for example, that we're moving through time, and the universe is changing its configuration at every time, time is flowing, who's to say what the events on that simultaneity plane are? I have my simultaneity plane, but Dr. Ashburn has a different one. And this makes us realize, well, wait a minute, what did I mean when I said time was flowing? Maybe what's happening is that there's just a space-time, there's just a set of events, future, present, past, here, there, and everywhere, and they're just all laid out once and for all. I mean, after all, a few weeks ago I was in London. Now I'm in Oxford. London didn't disappear because I'm not there. Why should the future and the past be any different? Just because my present state puts me here in time, what about my future states? What about my past states? Is there a flow of time at all? Does time flow? Or are all the events in the history of the universe, here, there, and everywhere, simply one given fact? Temporal duration. Now we're back to the issue of the second property of clocks, which is that they're stopwatches. They measure the duration of time, measure it in some sense. Well, in the end of the 19th century, Fitzgerald, who made very important contributions to the birth of special relativity, one of the great Irish physicists, a great ether theorist, wrote a wonderful paper about standards in physics, standards of time, standards of length, and so on. And he said, what is the most accurate clock you can lay your hands on? At the end of the 19th century, what was the most accurate clock? And he said, well, you have to go to the astronomers, because the astronomers use the rotation of the Earth. That's your standard of time in astronomy. You don't have a better clock. But there's a rub. First of all, if you calculate backwards using the rotation of the Earth, you're going to predict the wrong times for the ancient eclipses. Secondly, you have a theory about the Earth. And you know that the Earth is covered in oceans and that they have tidal effects and that produces friction. And that's going to affect the rotation of the Earth, because otherwise if the Earth was completely, utterly solid and wasn't interacting with anything in the universe, conservation of angular momentum would mean that it spins constantly at the same rate. But it's not a completely solid object. I mean, it's got structure, it's got surface tides and so on. Now, if you take the tidal consideration, tides into consideration, it turns out you would predict something more than a 5-hour gap, which is the gap between what we think the time is now and what the time of the ancient eclipses was. Let me put it this way. When I calculate backwards when the ancient eclipses should have been something like 3,000 years ago, I get a 5-hour discrepancy. If I take into account the role of tides on the surface of the Earth, I don't get exactly 5 hours. There are other effects as well. In fact, the other effects are going against the slowing feature of the tides. And these are things like sea level changes, the amount of ice on the surface of the Earth, the sea level rises. There's an exchange of angular momentum between the molten inner core of the Earth and the mantle of the Earth. It's hugely complicated. And nowadays people are trying to reconstruct how the past times were changing relative to the rotation of the Earth, and it turns out to be an extraordinarily complicated matter. And it's not just the tidal effects. But then Fitzgerald was asking, but look, we know that the Earth can't be a perfect clock. Well, what are we going to do? Well, Einstein came along, of course, in 1905. We're trying to understand what temporal duration is. And Einstein said, well, you measure the idea, you measure the time duration between events by using perfect clocks, ideal clocks. And this raises the question, well, what's an ideal clock? Why, for that matter, is this thing on my wrist a better clock than this thing in my chest that's also ticking? Now, if you think you know the answer to this, you probably don't. It's a tricky one. What makes this more regular than that? All right. Now, another point of view, which actually is much earlier and goes back to Newton at least, that was defended also by Fitzgerald, Poincaré, and now Julian Barber very prominently, ideal clocks are actually defined by duration. It's the other way around. Well, what is duration in that case? Well, here you have to appeal to the basic laws of physics. They tell you what duration is. It's the temporal parameter that appears in the equations of motion, the field equations and all the fundamental equations in physics. That temporal parameter, you choose the one that makes the equation simplest, and that's what defines duration. Now, I'm going to leave it there because Julian is going to come back and say a lot more about this, about what a clock is and its relationship to the laws of physics. Duration and motion. I want to start with a parable. The famous professors Kaluza and Klein, great friends, who I hope are here today. This morning I heard that they were in Carfax having a coffee together. And Professor Kaluza decided he wanted to get here early to get a good seat. So he walked more or less directly north along pretty much a straight line and arrived at St. Cross. But Professor Klein said, no, I think I'm going to go to Blackwell's. I've heard this book called The End of Time by Julian Barber, and I think I'm going to buy it. I don't care so much about having a good seat. And of course, they meet up again, and Kaluza talks to Klein and says, well, I got here before you did, and the distance was shorter. And Klein says, I know the distance was shorter, but wait a minute, we're scientists. How would you prove that? Of course, a crooked line between 2 points in Euclidean geometry is longer than a straight line. But how would you prove it? How would you measure it? Well, nobody has tapes that long, for example. So what you could have done is Professor Klein could have gone to the Museum of the History of Science here in Oxford on Broad Street and found what's called a Waywiser. Well, that's it doesn't come out well, but it's a device that rolls along the ground, a wheel that rolls the ground, and the number of rotations is registered on a dial and converted into units of length, furlongs or something, whatever it was they were doing in the 19th century. And by the way, I promised Benjamin Franklin would appear. He also developed, amongst its many inventions, an odometer in the 1760s that would attach to a carriage, the wheel of a carriage, and record the number of revolutions that would translate into distance. And the nicest one of all, seems to me, is this, again, a Waywiser, the late 18th century, that's also in the Museum of the History of Science. So you can use these devices to actually measure the distances and confirm Euclidean geometry. But please take a look at this thing. What does that remind you of? Looks like a clock. Bear that in mind. Now I want to consider a different situation. They're at Carfax on some other day, they're having coffee together, and Professor Kaluza decides he's going to stay there while Professor Klein goes towards Blackwell's, maybe to go to the Museum of the History of Science, and then come back again. And they're going to compare their clocks. They have started with synchronized clocks. Kaluza is staying at home, and Klein moves out to Blackwell and comes back again. If they start with synchronized clocks, are their clocks going to be synchronized afterwards? Well, this is where Einstein comes in. Well, it's not just Einstein. He wasn't the first to see this, but he certainly organized the notion in a systematic way. Now I'm going to talk about a space-time diagram. That triangle is now replaced by a new triangle, where instead of space going up this way, from Carfax to St. Cross, now it's just time. So Kaluza is moving up the time axis. He's not going anywhere in space. And he's measuring the time on his clock, and there's the first tick, second tick, third tick, and so on. It's waiting for Professor Klein, who's moving out in space to Blackwell's, and then turning around and coming back again. Now, Of course, the trick is Professor Klein is in some sort of super-duper rocket that's moving pretty close to the speed of light. And it turns out, if he's going the appropriate speed, Professor Klein's clock will tick once, twice, 3 times, 4, 5, 6. Whereas Professor Kaluza's clock went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is a fact. This is being tested. This is the famous phenomenon of time dilation. And you look at this diagram and you think to yourself, gosh, that reminds me of the previous diagram. Maybe there's a geometry of space-time. And maybe a clock is a waywiser of space-time. Is measuring the distance in space-time. And that's exactly what a clock is. You see, the guy who developed this clock, this waywiser, had a premonition of relativity, because clocks are waywisers of space-time. But now the geometry is strange, because the straight line has the longest length, and the crooked line has the shortest. And this is exactly what we mean by Minkowski geometry. It's not Euclidean, but the clocks are, as it were, measuring something, a property of space-time. Are they measuring it, or are they just doing what they do? And we talk about Minkowski geometry as a way of talking about what they do. The extraordinary, extremely important thing about time dilation is that it's universal. It does not depend on what the clock is made of. This is one of the most remarkable things in physics. A clock will dilate independent of its constitution. It doesn't matter whether it's made out of wood, what its constitution is. Every well-working clock will dilate by the same amount. Of course, what happens when it accelerates, for example, when it has to turn around, or when it comes to stop here, that will depend on the constitution of the clock. Take your grandfather clock at home and run around the street with it and see if it's good for it. But on the other hand, if you will put your grandfather clock into uniform motion, it will dilate just like any other clock. Finally, gravitational time dilation. Well, this is something that really was something that Einstein discovered between 1905 and 1915. And this is simply the effect that when I have a clock on this is supposed to show the surface of the Earth, and this is supposed to show the same clock somewhere vertical, some vertical height above the surface of the Earth. And then it turns out, thank you, then it turns out that the same clock measuring the same phenomena, the passage of time for the higher clock passes quicker. So in other words, the workings of a clock, no matter how good you make these clocks, no matter how accurate they are, whatever that means, they're going to function differently at different heights in the Earth's gravitational field. Now the irony here, this is another fact, and incidentally, we all have familiarity with the GPS systems, whether they're on our smartphones or on our cars or whatever. If you want to get accurate readings on GPS, the fact that you get accurate readings means that the atomic clocks functioning in these satellites and your receivers and all the rest of it, they compensate, they take into account both relativistic time dilation and this gravitational effect. If they didn't, you wouldn't get the right readings. This is not just theory. This is day-to-day practical technology. The irony, of course, and for physicists, I mean, this may mean something. We call this a gravitational effect. This is very dubious. It depends on what you mean by gravity. And in Einstein's theory of general relativity, which was his theory of gravity, the word gravity is very, very difficult to understand. I mean, it doesn't have a well-defined, it's not a single thing. And very often we say, for example, well, gravity is the curvature of space-time. It's not a bad definition. It's as good as any other. In which case, this is not a gravitational effect. This has nothing to do with the curvature of space-time. Well, finally, we get to the really, really interesting question that philosophers love to talk about. What ultimately is the difference between space and time? Well, I've run out of the ladder. Thank you very much. And I'll leave some references for you.
So we've got plenty of it, whatever it is. Questions?
we normally explain, well, I use explain in a bit of commentary, we explain the present by reference to the past. But if you say that an event A in physics, that this idea that event A can cause event B only if it precedes it, if you say that's only an interpretation of the formalism of physics, it doesn't necessarily follow from it, then why not explain the past by reference to the present?
Very good question.
Is that a stupid question?
No, it's a very, very good question. It's a very good question. Remember, I mentioned before that the fundamental laws of physics, at the most fundamental level, are time, reversal, invariant. They don't know the difference in the future and the past. But we have this fundamental notion on a day-to-day basis of things causing things, causal effects, and they're extremely time asymmetric. Virtually by definition, a cause is prior to the effect. Virtually by definition. That notion is folk physics. It's not fundamental. At the fundamental level, what's really going on is something like this. Suppose you have a Persian carpet laid out on the ground. And you're studying this carpet, and you're looking at patterns in the carpet. And you think to yourself, well, I'm a scientist, I should be able to figure out these patterns, I should be able to write down an equation for the patterns. Let's test it. Somebody produces a very small strip of the carpet, with all the colors on that strip, and hides the rest of the carpet. Can you predict the rest of the carpet, what it looks like, just from a slice? Okay? Well, you should be able to if you've got the right equations. And that's the way it works in physics. The slice is now a time slice across the universe. And if you've got the right equations, you can use the information on that time slice to predict both the future and the past. Just as the way that in the carpet you were able to predict one side of the carpet as well as the other side. And that's the way that it ultimately works in fundamental physics. So you could say that at a fundamental level, the present, insofar as it's causing the future, is also causing the past. But actually, go back to the issue of the carpet. It's not that one part of the carpet is causing the rest. It's just that there's a pattern. And that's essentially what the laws of physics are. They're patterns in the universe. The idea of causation is something we build up on the basis of, again, Reichenbach, the great philosopher, pointed out, you're not going to get really a notion of causation off the ground unless somewhere along the line you introduce an arrow of time. Because then we can distinguish between the past and the future. We can talk about causes being prior to their effects, and that it ultimately rests on these thermodynamic, these entropic properties of the world. And these only come about, this entropic hour of time, this thermodynamic hour of time, for example, entropy always increasing, never decreasing, only comes about because we're dealing with objects that have many, 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 many degrees of freedom, many, many particles, and like gases and people like us. But at the fundamental level of microsystems, for example, you don't see an hour of time. And you don't see causes and effects. This is something that only arises at a much, much higher level with many, many systems with many degrees of freedom. I don't know whether that was helpful.
Yeah, that's helpful. Thank you. I just wondered about
It's a very good question.
I'm going to bring up probably the thing that somebody's going to do is audience first. Quantum mechanics, where you've got instances that can happen in, sorry, that's the wrong way of phrasing it, and you'll probably correct me because my physics is appalling, but where the same two different things can both happen.
Yeah.
Does this mean that, I know the two theories aren't really that compatible at the moment, but does this mean that there can be more than one time dimension? Is there an element to this?
Yeah.
Try and squeeze quantum mechanics with this idea that you know, the Schrodinger's cat is both dead and alive and everything in between.
Right. Well, you touched on this little topic called understanding quantum mechanics, which would take an enormous amount of work to look at the different ways that people try to understand the foundations of quantum mechanics. But when you talked about, for example, Schrodinger's cat, quantum mechanics is all about and rather than or. It sets up a situation where it looks as if what you're predicting is the cat is not, it's not that the cat is either dead or alive, it's both, it's and. That's the so-called principle of superposition. You can't get around it. So what's going on here? Well, how do people interpret this? Well, some people say quantum mechanics breaks down at the level of cats. Some people say, oh, well, the reasoning that you were using, which is essentially the Schrodinger equation, which has got time built into it, but a single time. At some point, that's going to break down, and you're going to have what's called a collapse of the wave function, and then you'll get an or rather than that. If you drink enough water in Oxford, and particularly around the philosophy faculty, you'll find that an awful lot of people take the and seriously. And this is the so-called many worlds interpretation, the so-called ever interpretation. So what's really happening is there is a cat that's alive and there is a cat that's dead. But they don't see each other, because these aspects of the world sort of branch out and have no causal contact with each other. Gosh, I used the word cause. Anyway, they have no causal contact with each other. So you get a multiplicity. But that doesn't mean that there's many dimensions of time. There's still one notion of time. It's that the universe has a kind of branching structure. Now, that branching structure does look time asymmetric. But that's because we're dealing with very large systems again. Cats are large systems. Apparatuses are large systems. We're large systems. And we're inside that branching structure. So every time you're looking at the cat, actually there's a version of you seeing the cat alive and there's a version of you seeing the cat dead. Sorry about that, folks. That's just the way it is in this interpretation. But it doesn't necessarily mean that there's many dimensions of time. There's one dimension of time. And with respect to that one dimension of time, the universe has the branching structure.
So you're quite categorical to say there's only one dimension of time?
Yeah, I mean, the minute you start introducing multiple dimensions of time, it does a lot of havoc to your fundamental equations from physics. Yeah.
Thank you.
Thank you.
Am I correct in saying that Einstein believed in the block universe? And what is your thought about that?
Yeah. There's a famous letter he wrote when the wife of his closest friend, Michel Besso, died just before Einstein's death. He wrote to her saying, if it's any consolation, the difference between the present, the future, and the past is illusory. Now, I don't know how much consolation that was. But here he was essentially saying, yes, he doesn't believe in the flow of time. I tend to think this is correct. And it's easy to live with because it doesn't make a darn bit of difference to any of your experience.
Is that a conventional view of physics today?
I wouldn't like to speak for physics in general. I would say that it's controversial within philosophy. There's a lot, in fact, we have a colleague here who works precisely in this area, in fact, several. And it's controversial. There are arguments for and against.
So,
Thank you, Nick.
I wonder if it is quite correct to say that the arrow of time, irreversibility, has to do with thermodynamics. What of Popper's point about throwing a stone into a pond and the ripples spread out,
Yeah,
that they never spread in,
Yeah.
and up comes the stone.
yeah.
You could say then that the water is made of lots and lots of particles, but on the other hand, you could have a similar thing happening at a fundamental level, where you get a wave spreading out from some event,
Right.
and never the reverse.
Well,
Which
yeah.
suggests that
Yeah.
it isn't really.
Yeah, I mean, when I say thermodynamics, I'm being a bit imprecise. It's not thermodynamics per se. Thermodynamics is describing these phenomena. It's certainly true. For example, take the case of what's sometimes called the electrodynamic arrow of time. A source of electromagnetic waves generally produces waves that move out into space, but you don't see the same sort of thing of these waves converging spontaneously onto some source. But the equations allow for the latter. So we're back to the old problem again. At the most fundamental level, every process you're seeing happening in time, the reverse process is also possible. So why don't we see them? Why don't we see them? Well, because it's not the laws themselves that are telling us, giving us the answer. They're time symmetric. It ultimately has to do with initial conditions. It's the way the universe was set up. It has something to do, ultimately. I don't like to use the word initial precisely because of your point. There's really nothing special about initial conditions as opposed to the conditions at any time in the universe. But the point is that there's something over and above the laws. The laws describe what will happen under certain circumstances. Who decides what the circumstances are? Nature. And the circumstances are that you don't see these converging waves in electrodynamics. You don't see them in ponds, for example. But they're perfectly good solutions of the equations. Now, of course, when we see these processes acting out in terms of heat engines and so on, well, then we talk about thermodynamic entropy increases. But it's not that thermodynamics explains any of this. Thermodynamics is merely describing it. But so nature giveth and the Lord giveth and the Lord taketh away. He gives us the equations, which predict an awful lot, but unless you put in conditions somewhere along the line, sometimes called initial conditions, or in physicists call them Cauchy data, unless you put in the data somewhere, all the equations describe as many, many, many possible histories of the world, each consistent with the equations. What picks out our world? Well, nature. But you are there.
Yeah.
It's just a different you.
Is there somewhere that we are all children somewhere?
Yeah,
That's a
absolutely.
fascinating idea. But I'm conscious of being here now.
Right.
But my consciousness then is not a slice as well.
But in 5 minutes' time, you're going to say exactly the same thing. I'm conscious of being here now. You just have to imagine that there's just many versions of you. In some sense, there's many versions of you. You're all coexisting. And each version of you is aware of a particular instant in time. That's all. Incidentally, this isn't so far away from Everett. Because remember when Everett said there's many versions of you, one seeing a cat, one seeing alive, one seeing a cat dead? That's not so widely different from the notion of time itself. It's just that now we've introduced another kind of multiplicity in the world. Time itself is a kind of multiplicity, as I mentioned at the very beginning. And Everett just said, well, you got part of the multiplicity, not all of it. There's also the branching universe.
So that was the way with causation. My PhD is on mental causation, but if
Right.
physics, if there's folk physics in terms of causation, then that
No, but causation is a very important notion. It's extremely important, probably on ethical grounds and moral and legal grounds. I mean, after all, if we do away with the notion of causation, what do we make of people's responsibility in life? How do we bring them to heal, as it were? To stand responsible for their actions in the legal courts. No, it's a very, very, very important notion. It's just not something you find in the fundamental equations of physics.
Question?
So, could you repeat your question?
Discrete space-time, discrete. And not continuous, but discontinuous time.
Is space-time discrete?
Yeah, just
Is space-time discrete? Many physicists think so, particularly because of problems with quantum mechanics and quantum gravity. Many, many physicists think that the space-time continuum is actually discrete. There are atoms of space-time. I think the jury is out, myself. I think the jury is out. Using space-time as a continuum has proved to be enormously useful mathematically, particularly in Einstein's theory of general relativity, his theory of gravity. It's enormously helpful. But whether it's correct, we don't know yet. You know, people often talk about the so-called Planck length in space and the fact that if you go down to very, 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 very tiny distances, much, much smaller, for example, than the width of a proton, much, much, much smaller, then all hell breaks loose because of quantum effects and you can't even talk about distance anymore and all these things. Well, let's see, let's wait and see. It seems to me the jury's still out. That's my own opinion. That's not inconceivable by any means.
Yes.
Sorry, I was wondering, sorry to kind of repeat a question over here, but I'm still wondering about this notion of consciousness and the privileged direction with which we experience it. So would you attribute that to this macroscopic
Yeah.
this macroscopic,
Yeah.
why we experience
Yeah.
this privilege.
Yeah. Just a point maybe to clarify this a little bit more. Here we are sitting at this instant of time. And we think to ourselves, we have access to the past, but we don't know the future. We don't have access to the past. We have access to our memories. And our memories and all the records of the past are in the present. We have access to the present. But the present itself, like the picture of Einstein's office, tells an asymmetric story. It gives us information about the past if we interpret it right. There's a lot of theory here also. That instantaneous photo is like a memory. It gives us information about the past if we interpret it right. That's how we know about the past. We infer it from the present. But we don't do the same kind of inferential procedure for the future. And because, again, when we form memories in our brains, for example, information is coming into our brains to create, some part of our brain goes into a non-equilibrium state. There's an effect of that information in our brains, and our brains rapidly equilibrate and form stable memories, stable states, more or less stable states over time. And that process of stabilization, of equilibration, is something that it's a feature of the world that we don't, has to do with, the, as I said, the configuration of the world. Things equilibrate into the future, not into the past. Or at least that's what we call the future and the past. But this equilibration process is time asymmetric. It's, again, linked to the entropic arrow of time. If we didn't have such an entropic arrow of time, there would be no intelligent life, because you have to have memories to act intelligently, to cope with the world. Intelligence requires information about the past, because you're using information about the past to know how you're going to act in the future. So you have to have what physicists call an entropic gradient.
So would you say that those decisions would be free in some sense? Like to...
Well, freedom of the will, I mean, that's another issue altogether, because what you're really asking is our sense of free action, freedom of the will, consistent with the fact that the fundamental laws of physics are deterministic? Sometimes people say that quantum mechanics is indeterministic, but that itself is debatable. And even if it were indeterministic, it's not really going to add anything that's interesting from the point of view of free will. So the question is, if we're living in a mechanical universe, what are we? Well, we're biological machines. Unless you're a dualist like Descartes, unless you think we have a soul that somehow transcends all the material aspects of our brains and so on. But if you think that we're basically biological machines, as Einstein once famously asked, when you make a decision, do you suspend the laws of physics in your brain? No, your brain is acting out part of this great pattern in the world, which is described by the laws of physics. But we have the sensation of free will. And we have a notion of personal responsibility. And they're super important. And they're completely consistent with the idea that the world is deterministic. Well, I'm sure that if there were some other philosophical colleagues here, they would dispute what I just said. But it's called the compatibilist approach, that the world is deterministic at the deepest level, but we have effectively a solid, robust notion of free will despite that. It's called the compatibilist position, and I'm going to subscribe to it.
But so that would say fundamentally, even though you think you're using past information to guide your future actions, you're not really in a fundamental sense.
Well, your brain is certainly using memories, for example, when it's making decisions. It's certainly referring to past experience. I mean, from the first day of an infant's life, it's learning about the world and it's acting on that learning. It's a little inductive machine. So that child, even though that child doesn't have consciousness in the way that we do, or animals, for example, particularly in their infancy, they don't have consciousness the way we do, but they're learning all the time.
This question.
When one is thinking about the multiple worlds, it's easy to imagine a branching tree. It's intuitively obvious.
Yeah.
But could that also apply to the past? Could there be many pasts which lead to the single present?
Very good question. Well, suppose the universe were in a box. If the universe were confined to a finite space, there's a thing in quantum mechanics called the recurrence theorem, which tells you that no matter what state you find yourself in at the moment, no matter how many branches there are, for example, in the universe, and the universe continues to branch, eventually you're going to come back arbitrarily close to that initial state. Probability 1. Which means that there's going to be a recurrence. Which means that if the universe now is branching that way, eventually the branches are going to have to coalesce. The time scales involved are, to use the word stupendous doesn't give it justice. Zillions and zillions and zillions of times greater than the age of the universe. But it's a fact. Of course, we don't really think the universe is in a box. So whether the recurrence theorem is really applicable to the universe as we understand it at the moment is highly debatable. But the point is that, yes, in principle, if the universe was finite and all of its structure was fundamentally quantum mechanical, including gravity, then yes, at present we observe a branching going forwards in time, but eventually these branches would coalesce back again. Of course, now the entropic gradient would be pointing in the opposite direction. So what would sentient beings, how would they understand the world when the branches are coalescing? They could live on the entropic gradient, they just say that our future is their past.
We'll have to be quick with our final two questions. One here and one there.
Yeah, I've been wondering, would it be fair to say that time is a function of the Higgs field on the basis that if things didn't have mass, presumably everything would travel at the speed of light and time wouldn't exist?
Well, when you say that everything would travel at the speed of light, that's finite, which means that photons and whatever else doesn't have rest mass would travel a certain distance in a certain time. So time exists. Even if everything's moving at the speed of light, time would still exist. It's just that we all know, for example, because of time dilation, that as you're approaching the speed of light, time seems to slow down. But that notion of slowing down is a subtle one. It's a very subtle one, because if you're actually in the laboratory that's, according to somebody else, approaching the speed of light, time seems normal. Otherwise it would violate the relativity principle. So it's a very subtle notion. Time dilation, like length contraction and special relativity, are very subtle. In a sense, they're appearances. And yet, they lead to Professor Kaluza and plus Professor Klein having non-synchronized clocks. So there's something real about them too. When you're teaching this stuff, it's very difficult to get across exactly how to put this effect. Because words, and very often in physics, words don't do justice to the mathematics. The mathematics are more or less clear. I don't know whether that answered your question. There's still be time.
And one more question.
Yeah, it's a question about gravity and electromagnetic radiation and time, velocities and so on. I'm just wondering in my own head, we know the velocity of light is limited. Information can't go any faster. Nothing can go faster than the velocity of light.
We think that's right.
Sorry?
We think that's right.
Yeah. Okay.
It's not actually a theorem.
Okay. We think that's right. We can even calculate that velocity looking at the magnetic properties and the electric properties. Why do we think that gravity in itself is limited to that speed limit? It's not infinitely fast, we know that. But why is gravity limited?
Oh, because one of the great discoveries that Einstein made was the existence of so-called gravitational waves. You remember that recently there was this extraordinary, absolutely amazing experimental result. Well, the theory tells you how fast they propagate. So the very theory that predicts their existence tells you how fast they propagate. And they propagate no faster than light. In fact, they propagate at the light speed, essentially.
Okay, but I was trying to work out in my head. I appreciate all that.
Yeah.
I'm just trying to work out in my head. Electromagnetism, I can see where a figure for the velocity of light would come out of. With gravitation, I don't know. Perhaps I don't know the theories, I don't know, but why are they the same speed?
I'm not sure that I can tell you in a few lines.
Okay.
I'd have to think about it. Maybe Julian would like to say something.
In fact, it turns out that it's almost impossible not to make them the same. That's quite deep in the structure of the theory, but it turns out that you have a universal light cone as it's turned out. That comes from the gravity, in some senses, bullies the other fields into having the same one. It's all so intimately interconnected. That's the reason, really.
So it's the ultimate speed limit, information, rather than electromagnetism and everything else. You just the speed of it, fastest speed.
I suppose you could put it that way.
You could, but information again is a subtle thing, and it's not clear that it's really physical. I mean, within the field of quantum mechanics and in quantum information theory, there's a big slogan nowadays that information is physics. But this again is very, very debatable. It's just that you can't create signals. You can't send. I mean, signals, as it were, carry information, but that's not their fundamental role. Information has something to do with agents. Signals either propagate it at some kind of speed or they don't. And the theory, both in in general relativity, as Julian said, gravity in its structural form in the equations tells you that the gravitational waves will move at a certain speed. And then there's the condition in general relativity which tells you that the non-gravitational interactions also travel at a maximum of that speed.
Well, in the last couple of minutes, we've started to anticipate our future speaker. But before we reach that particular future, I think we need to thank our present speaker once more.